Hello everyone, my name is Teresa Paneque and today I will be speaking about the work that I developed during my master's thesis at Universidad de Chile under the supervision of Professor Laura Perez and alongside all of these collaborators which will also be part of a soon-to-be submitted and published work. This is a kinematic and multi-wavelength study of the spiral structure in the protoplanetary disk around star Elias 227. So just to put this work into context with this conference, which is 5 years after HL Tau, I would say that the most important thing that we found out with ALMA and with the image of HL Tau is that disks have structure. And currently we know that this structure is not only rings and gaps, but can also be cavities, it can be arcs, and it can be spirals. Now, structure in disks is expected, and it can have many formation mechanisms, either perturbations from conditions of the disk itself, dynamical interactions, or condensation fronts. In this study, we will be specifically aiming to study the origin of the spiral structure around Elias 227, which is the disk that you can see there highlighted in the red box. Spiral structures in protoplanetary disks have two distinct origins. They can either arise from companion disk interactions, whether that companion is unbound, such as the case of stellar flyby studied by Nicolas Cuello, or if it is bound, which can be due to a binary companion or a planetary companion. On the other hand, spirals can also arise as a consequence of gravitational instabilities, which are expected in massive and cold disks. A way of classically studying if a disk is prone to gravitational instabilities is through the computation of the Tumber Q parameter, which is indicated there in the bottom. In the case of Elias 227, we will be trying to determine if the spirals are due to either a planetary companion, because there is no other star or object that has been detected in the nearby field, or if the disk is suffering gravitational instabilities. There are dust signatures that we can search and analyze for in order to answer this question. If the disk has gravitational instabilities, then we expect the spiral alarms to trap and grow dust. We will be able to test and to detect these signatures of dust trapping and growth through the analysis of spectral indices or through the analysis of contrast curves. We expect the contrast to increase with wavelength at the location of the dust trapping signature. This has been studied in vortices by Paolo Gazzoletti. On the other hand, the spiral morphology can also give us hints to the origin. If the spiral has symmetric spirals that can be adequately fit using a logarithmic spiral model with constant pitch angle at all radii, then we would expect the spirals to come from gravitational instabilities. On the other hand, companion-induced spiral arms are not expected to be symmetric, and their pitch angle should vary with radii within a single spiral. There are also kinematic signatures for gravitational instabilities, such as the GI wiggle, which has been predicted by Cassandra Hall. This will be a strong feature co-located with the spiral arm that will range over a large amount of velocity, so we will see it throughout many channel maps. Unlike planet-disk interactions, which will also create kinematic deviations, but these deviations will be localized. And we expect the amplitude of these deviations to be around 15% for a 1 Jupiter mass planet. Elias 227 has been studied at high angular resolution. It was one of the D-sharp targets. It is a class 2 stellar object. It has a stellar mass of 0.5 solar mass and a large disk to star mass ratio of 0.3. We expect GI to be an acting mechanism from disk to star mass ratios of 0.1. However, its Tumber Q parameter, its instability parameter, has been calculated to be within the stable regime by Laura Perez in 2016. It has two large spiral arms that have been computed to be symmetric at high angular resolution, and it also has a dust gap, which is located at around 70 AU. And this is not a prediction for gravitational instabilities. In this study, we will be presenting new band 7 and band 3 data at comparable resolution with the 1.3 millimeter data previously shown by Laura Perez in 2016. And we will also be presenting kinematic tracers, 13CO and C18O, at a transition that will allow us to avoid the cloud absorption, which has been a feature that has not allowed previous studies to study the kinematics of Elias 227. And of course, what we want to answer is, what is the spiral arm origin? Is it induced by planetary companion or is it induced by gravitational instabilities? We will start with the dust spiral structure of Elias 227. These are the observations that we will be using in this study, the new 0.89 millimeter and 3.3 millimeter data, additional to the 1.3 millimeter data that had been previously published by Laura Perez. We are showing this in brightness temperature so that it is easier for comparison. What we do is that we compute the subtracted images by subtracting the azimutally average radial profile to the previous images that I showed. This will allow us to enhance the spiral structure and be able to trace it to innermost radii. We do this and we deproject the radial distance of the spiral arm, tracing the maximum of emission along the spiral arm that we can see in the images. And we afterwards fit using MCMC chains a logarithmic model to obtain the pitch angle of the spiral arm. The pitch angle is fairly similar at a single wavelength. So between the northwest and the southeast spiral arm, we see that the pitch angle values maintain at around 13 degrees. And these values are also similar across wavelength. So we are seeing symmetric spirals. Now, these are values that are around 3 degrees less than what was computed from the high resolution D-sharp images. We believe that this is due to the beam difference. We have 4 times worse spatial resolution, and this can induce errors when measuring this very specific tracing of the spiral arm. We also compute contrast measurements. So we do this by comparing the flux at the location of the spiral arm as traced by the best fit parametric model in each wavelength and comparing it to the flux at an interarm region, which will be located 90 degrees from the spiral arm as traced by the best fit parametric model. We see, for example, that the peak contrast in the north spiral increases as we go to higher wavelengths. And again, an increase in contrast is expected when we have a dust trapping structure, as has been shown in vortex studies by Paolo Gazzoletti. I will now present the results from tracing the gas distribution with CO isotopologues. These are the channel maps of the 13CO and the C18O data that we will be using. We note that there is still absorption affecting the east side. This is specifically seen in the high velocity channels of 13CO, but also in C18O in less measure. There is also a north-south brightness asymmetry, which will be important. And I want to note that these images were taken and imaged in such a way that we would highlight the disk emission. If we image the data using an actual weighting, so a robust parameter of 2, and looking at the whole field of view, what we will see, especially at high velocities, is that there is a large-scale emission that coincides with the high velocities of the disk emission and ranges for many channels. Now, this large-scale emission cannot be adequately studied in this work because we lack of the specific UV coverage that we would need. This is why it looks like a stripy pattern, because we do not have the short baselines that we would need to have in order to properly study this large-scale emission, but it will be important for our conclusions. We decide to trace the emission layer only by using the emission that highlights the disk emission of both isotopologues, and we do this by applying the method developed by Christophe Pont in his 2018 paper, which consists in tracing the uppermost layer of the emitting surface and assuming that it is coming from a cone-like structure. Then by applying geometrical relationships, we can recover the height profile at a certain radial distance from the star. So we do this and we model the height as a double power law, differentiating between east and west sides of the disk. We note and we see clearly that there seems to be a height asymmetry between the emitting surface at the east channels with respect to the semi-minor axis of the disk and the west channels of Elias 227. This is also seen in the integrated emission maps because we see that there is a difference between the extension in the east and in the west. And the east are the channels that we trace to be closer to the midplane. So it makes sense that when projecting them, then they will appear to be the side that has a more extended emission, a more extended radial emission. But this is really because the height profile is closer to the midplane. Additionally, we study the channel maps and we detect multiple perturbations and features that range across many velocities. So we see innermost kinks that coincide with the spiral arm location, and these are present both in 13CO and in C18O. And we also see this curved pattern more to the outer radii that we believe is produced by emission connecting the upper and the lowermost emitting surfaces of the disk. We decide to compute SPH simulations of a gravitationally unstable disk because we are seeing tentative dust trapping signatures and also seeing multiple kinks in the channel maps. So we compute multigrain phantom SPH simulations. We will afterwards post-process this with radiative transfer code of MC-FOSS developed by Christophe Pont, and then to create mock ALMA images and be able to compare these models to the observations, we will use the exact same UV coverage as the observations, applying the tools available in the Galario codes developed by Marco Tassari. So we will vary this to star mass ratios. We will use ratios of 0.2, 0.3, and 0.5, and also the density profiles using a tapered power law and a simple power law expression for our different models, trying to see which model is most similar to the observations in all three wavelengths by comparing the pitch angles that we retrieve. Our best dust simulation has a disk to star mass ratio of 0.3, and it has an exponentially tapered power law with an index of 0.1. Here is the model, and here are the observations. When we trace the spiral pitch angle as determined by our best fit parametric model, we also see that the value of the pitch angle is very similar, and not only the value of the pitch angle, but also the radial extent of the spiral feature. It radially covers more or less the same extension as the observations, which are here plotted in the black dots, and the colored dots correspond to the simulations. Overall, we have symmetric spirals that are present at multiple wavelengths. We detect tentative dust trapping signatures and are able to reproduce the dust spiral morphology with SPH simulations of a gravitationally unstable disk at using parameters that are very close to the observationally derived parameters. We note that the gas emission is not azimuthally symmetric in the vertical direction, and this is important because it is not a prediction either for GI or the presence of a planetary companion. And finally, we see multiple perturbations in the channel maps, which also seems to indicate that there is probably instabilities going on in the disk. We propose that there is active infall of material, and we say this based on this detection of the large-scale emission, which we cannot accurately study in this work. But infall, if it is an ongoing process, may also explain the perturbed emission layer, which is not explained simply by gravitational instabilities or the presence of a planetary companion. Future work on this source will include accepted proposal for cycle 7 ALMA data to analyze the gas but at a higher angular resolution. This may also allow us to say something about the dust gap that has been observed at high angular resolution studies such as D-sharp, and also, of course, observations aimed at tracing the large-scale emission. We would also like to do detailed models with infall and a warp, which, although I did not mention it in this talk, may also provide insights into what is going on with the brightness asymmetry that is detected in the kinematical signature. Thank you very much for your attention.